All right. Hey, everyone. So last time we left off, we were doing some examples for Newton's second law and some of the various forces that we have covered. I'm going to start out by finishing just a few examples, and then we'll go and finish this chapter. Okay, so first example we're going to do today is you are working as a delivery person and you're sliding a package down a frictionless ramp. This ramp is 1 meter high. So let's put the picture in also. This ramp is 1 meter high, and the package that reaches the bottom cannot be traveling faster than 2.50 meters per second. So otherwise it will break. What we want to know is what is the largest angle that we could tilt this ramp with the height being 1 meter. What's the largest angle that we could tilt this ramp so that it will slide the package down but not exceed 2.50 meters per second when it reaches the bottom. So let me start out by selecting, I always got to do this right in blue. So I always draw a picture first. We have this sort of diagram of the ramp and the package. So this is sort of, mid process. We're going to assume the package starts at the top of the ramp. It's going to slide the whole way down till it hits the sort of the end of the ramp. The ramp is angled. Let's write the angle in here. Some angle theta. That's all right. Okay, yeah. Come on in. We're going to start an example today. So we have this example of some forces. Let me restate the question. So in this example that we're doing, we are sliding a package down a ramp, and we want to sort of tilt this ramp to a position where it won't, the package at the bottom of the ramp won't exceed 2.50 meters per second. So what is, the largest angle we can tilt this at without exceeding that speed of the package when it reaches the bottom? We could assume that if it's traveling faster than that, when it reaches the bottom, it might just like tip over and break. So what is the largest angle? We're pretty much solving for theta right here that we're drawing. So I'm going to, I always start with a picture, and let's label sort of the forces that we were going over in last class. So we could always say that the force of gravity is pulling something directly downward. So I'll just go like this, directly downward. That is the force due to gravity. I'm going to say Fg. And that is a vector like that. Let me, for a moment, I'm going to zoom in just a bit more. And what was some other forces that we're talking about last time? There was a normal force, say force of something that is, in contact with something. So it's perpendicular to a contact surface. So the normal force in this case is not directly up, it's perpendicular to this surface that the box is sliding on. So the normal force is going to be pointing somewhere like that. You see that's just about perpendicular to the surface. Like this. So that's going to be F sub n for the normal force. All right. Now here's, our choice. We could either, find the x and y components of the normal force, or we could find the x and y components of the force due to gravity. Let's sort of maybe get used to shifting our perspective by finding the x and y components of this force due to gravity. So what do I mean by x and y? Typically, on all of our graphs, we've had x as completely horizontal and y as completely vertical. In this specific instance, get rid of that. In this specific instance, I'm saying x as parallel to the sliding surface of this ramp. So if I just tilt my head a bit, I can see that there is this dotted line that goes that way. That would be the force due to gravity in the y direction. So I could say, I think the book says y, it labels it as y. I could also label this as, in other books, I've seen it as perpendicular. There's this, perpendicular sign. It's up to you how you want to label it. So we have that, and then we also have, let me make another dotted line. F. This is the, the components of this vector right here. F of force due to gravity in the x direction, or the horizontal if I'm shifting my head. If you don't like this sort of writing x and y, that's where I would say you could use FG perpendicular, and this is FG parallel. So that's just sort of like two lines like this. It's however you want to, write it. For the, the problem, I'm going to keep it as x and y. So we're going to split these components up. But already you can see this is kind of a complex problem. I got to factor in where all the arrows are pointing. Let me make a free body diagram. Maybe that will clear things up. Maybe it'll make it easier to find, these values right here. So I'm going to, let's do free body diagram like right here. I'm going to try my best to keep the same tilt. Like that. So remember, a free body diagram is just a diagram of all of the forces with none of the surroundings. So I just draw a square because I like to keep an idea that this is an object that has one force pointing this way. It has one force pointing straight down. And we had this, I broke it up into pieces already. So like that and like that. Let me just y, x. What is the, there's no angles in here. This is where we could just use some properties of geometry. We can see that the angle of the ramp is going to be the exact same angle as this side of the triangle right here. So that is the same angle. That is very helpful solving this. Let me slide that over just a bit. And then I'll zoom out if you wanted to take a look at the question again. Just like that. Okay. Now let's, write out the forces, split them up. I guess I can, before I do this, let me label what these components are going to be. I think we've all seen this quite a few times by now. But the x components and the y component are just, sections of this triangle. Let me do it for this specific one. So in this specific instance, if, in the horizontal, parallel to the sliding surface, it is force of gravity, but this one is opposite. So that's sine theta. So this is the only tricky thing, is that they swap. Oops, sorry. F sub g times cosine theta. All right. I'll just put that like next to there. Now let's, write out all of these components. Let me find, well, actually, I don't have to do both of the components, right? So I'm only interested in how fast is the box skating when it's at the bottom of the ramp. So I'm only interested in this parallel component, the parallel to the sliding surface. So in this case, I can reduce my work, in half by saying I don't really even care about that perpendicular component. I'm just wanting this one. So let's look at just that component. Let's add up all of the forces in the x direction, or parallel to the sliding surface. So that's normal force in the x direction plus force of gravity in the x direction. And really that's it. So look on the free body diagram, there are only these two forces. That equals mass times acceleration in the x direction. This becomes just, there is no, since we've tilted the whole picture sideways just a little bit, there is no, looking up here at this normal force, there is no, parallel to the sliding component. There's no component this way. So this is 0 for the normal force. And for the force due to gravity, we have this. Oops, sorry. Try to make that smaller g, sine theta. All right, maybe this can be useful if we just find the acceleration in the parallel component. So let's rearrange this, just solving for the acceleration. So let's go acceleration in the x component is f of g sine of theta over the mass of this package. Okay. All right. Now, what else do we need? We have an acceleration. We want to know basically a final velocity right here. You know, we're starting out the box up here. I'm just loosely sketching. So we start out the box at the top of the ramp and it has no velocity. So we have an initial velocity. We want to find a final velocity when it's all the way down at the bottom of the ramp. And we now have an acceleration. Okay, so maybe we could use one of those kinematic equations from, earlier to solve for this final velocity. Let's first, before we do that, what would a final velocity down here look like? So first off, we need to set a limit. So we wanted this package to not go past. Let's see, it's right here at the top. So if the package reaches the bottom of the ramp traveling faster than this, it will break. So that's sort of our limit. So we need a way to sort of show this. Let's, with the same reasoning that we've found these forces, sort of splitting it up into components, parallel and perpendicular to the sliding surface. Let's do that for the velocity. So I'm going to say that the maximum velocity, we're tilting our head looking at this picture over here, can't be faster. We're going to input a value in here. That's going to be whatever that's, velocity is at the bottom times the angle, maximum angle that we're going to tilt it at. Sort of like a initial and final reasoning for me writing this. I'm basically writing this down so I can use it in just a couple steps. Now, we're going to use one of those kinematic equations from earlier. So we have, let's use the one that says f of x squared is equal to the initial, is v of x is equal to v naught of x squared plus 2a, the acceleration, times a change in displacement. So we're going to assume at the top, this initial velocity when it was at the top was 0. That makes this term go away. Or I could just put it underneath like that. And then we have 2 times a sub x. Well, we just found a sub x over here. So let's put that in this equation. We'll do that. 2 times, right, there was, oh, what did I, fg over m. Oh yeah, before I do that, it's a bit messy. I don't want to do over here. I forgot to break this acceleration down one more step. So what is force? in general. Force was mass times acceleration. So for force due to gravity, it's mass times acceleration of gravity times sine of theta over mass. And that's, we could see these mass terms cancel. So that's why we have this slightly more simplified version of that acceleration. I was wondering why there's no more force. Then this can go up there into the acceleration term. Okay, and that will be 2 times g sine theta times delta x. And it's right here where we see that we have a sort of issue. We know that the height of the ramp, h over here, was 1 meter. We don't know really how far it goes as it slides down the ramp. We don't know its x final and x initial as it slides down this ramp. But we do have that delta x term, and we have now a sine of theta in this. So we have basically the hypotenuse term, it's delta x, and we have theta of this triangle. What I'm getting at is that delta x times sine of theta equals the height of the ramp. And we already know the height. So that's actually useful, and it will simplify this equation even more. Okay, so after we've simplified this little bit, we get the final velocity as it's moving down this ramp is equal to 2 times g times h, so the height of the ramp. And now this is where you can see I'm going to put this value, or let me take the square roots first. Bx is equal to square roots 2g times h. So now we have this v sub x. Let's put that into that equation that I've written up here at the top. That's sort of me putting the limit on how fast this box can slide down the ramp. Okay, so we have this maximum velocity is just whatever speed it was going is connected to how steep the angle is of the ramp. I'm just going to put it in like this. So we have 2gh times sine of whatever that maximum angle is. So now at this point, you see we know what g is, we know what h is, we know what the maximum velocity can be, or it should be. So we know everything except the angle. That means we can solve for the angle. I'm just going to, after inputting the values, I'll do the whole thing. So we'll go 2.5 meters per second. 2 times 9.8 meters per second squared times 1.0 meters. All of this is times sine of some angle. And now from this step, I'll just skip because I don't want to rewrite it a couple more times doing this. We find out that the angle should be about 34.4 degrees. So if we angle the ramp at that, the final velocity at the bottom of the ramp will be 2.5 meters per second. All right, and we're going to do one more example and then move on to the last part of Newton's laws. So let's go down here, try to keep that in frame still, and I will have to shrink that. I see. Yeah. So let me go like this. How does that work? Let's see. Woohoo, that's good. All right, next example. A picture weighing 8 newtons is supported by 2 wires with tensions T1 and T2. Find each tension. This one is specifically related to a picture, so let me bring in the picture. Otherwise, it would have just had to specify the angles given. In this one, let's split up the problem into components. Before we do that, let's draw a free body diagram of this situation. So let me do it as just a dot this time. So we have force of gravity downward. We have T1 going, to the right, kind of like that. We'll say T1 right here. T2 going up, kind of like that. Let me get this. And we already know we're going to break this into components. Let's do it right here now. So we have this x component of, we have this horizontal component of T1. We'll call T1x. We have this vertical component called T1y. This one has T2x and T2y. What are the angles on this triangle, though? So from geometry, I have this. This is supposed to be, completely horizontal, or 0 degrees at the horizontal. So since this up here is 60 degrees, that means that this right here is 60 degrees. That's just going to be tiny like this. By that logic, that also makes this 30 degrees. Okay. So we have the sides of the triangles defined, and we have the angles given already. Let's split this up into its components. The sum of all of the forces in the horizontal direction. first wire and the second wire and force due to gravity. All of that equals mass times acceleration in the horizontal direction. Well, we know it's stationary. It's something that's just hanging there. It's not moving, accelerating left or right. So that makes this go to 0. So I'm just gonna say 0. Also, its gravity is not accelerating. The force due to gravity is not accelerating left or right. There are no components to this, or I should say, there's no horizontal component to that. 0. So all we're left is these two. Let me slide this over. Just realized it's going to take space. So T1 X, that's this thing. It's on the adjacent side of the angle. So we have T1 cosine of 30. And for T2, we have T2 cosine of 60. Let's, while we are here, we're wanting to solve for, well, actually, let's not quite yet. So I'm going to leave it like this. So this plus this equals 0, basically. Let's do the vertical components. The same exact thing, except vertical. We also know it's not accelerating up or down. So that's 0. I know that's going to be 0. Let me do that last. I'm going to run out of room if I do that first. So for T1 Y, that's going to be T1 sine of 30. For T2, that's T2 sine of 60. For G, that is just the complete force downward. But also, oh yeah, sorry. So this also applies for the X component. So since gravity is going down, that's going to be a minus. Things traveling downward are negative. So that's negative f of g. This equals 0. So what I was saying up here about the X component is that things traveling to the right are positive. Things traveling to the left are negative. So for this X component up here, the T1, that's positive. This should be a negative sign because T2 is traveling to the left. All right. So we have that equals 0. Now, here is the point where we could see that we have, some factors to solve for. We have 2 unknown variables in this equation and 2 unknown variables in this equation. And we're basically wanting to solve for these variables eventually. So let's just solve for one completely up on this X component. So let's solve for T2. What I mean is just rearranging this equation. T2 equals T1 times cosine of 30 over cosine of 60. So momentarily, that's what T2 equals. We've sort of solved for it just by adding it over. to the other side of the equation. Now that we've solved for it right here, let's put it into this equation. I need room over there, so I'm going to go like this, solve for it, put it in that equation. Okay, so we have T1 times sine of 30 plus T1 cosine of 30 over cosine of 60 times that sine of 60 still minus the force due to gravity equals 0. Now it's at this point where we know everything. We know force of gravity because that's just given as a value already. That's already given in a force in newtons. We also are already given these angles, so we could solve for T1 at this point. T1 equals 4.0 newtons if we were to do all this in the calculator. Now that we know T1, we can put it back into any of these other equations. We could say, I'll put this into that equation and solve for T2. So do that step down here. T2 equals 4.0 newtons times cosine of 30 over cosine of 60. We get T2 equals 6.9 newtons. All right. That's sort of finishing off or like rounding out that Newton's second law section. We're going to finish the chapter with this next page, and it's just some sort of conceptual reasoning. So let me go like that. So we're going to move on to Newton's third law. Newton's third law is basically, it says that every action has an equal and opposite reaction. I'm sure you may have heard that before. Here it's sort of written a bit more formally. If there is an object A that is exerting a force onto object B, then there's an equal and opposite force, and I mean opposite in opposite direction, from object B onto object A. Let me clarify with a little picture. There's a box on a desk. If I put a box, your book or pencils on your desk or your laptop, whatever, why doesn't the box just continue going down, pushing the table down into the ground, forever downward until it reaches the center of the earth? Because the box, it's exerting this force down, but the table is exerting a force up, and it's an equal and opposite force. So just in general, these are just sort of placeholder indices. So the force of one thing onto another is equal to minus the force of the second thing on the first thing. So for my little, analogy, box table, the box is making a force downward. So this is the force of the box on the table. So if I did this with indices, it'd be like FBT or something. There's an equal in magnitude, but opposite force supplied by the table. So this is the force of the table on the box. That's sort of, maybe you could see this would be TB. Indices are just flipping. That's sort of what this is showing. Okay, so there's always this equal and opposite force. If I was to push something, why is there ever anything moving though? We have, say I wanted to, slide a box on the ground. If there's going to be an equal and opposite force always, how is the box able to move at all when the forces may seem to cancel? I have a little example for this. So how do things accelerate at all? So I like reusing pictures I've drawn. So we have this dog pulling the sled. Same sort of principle. Why is the sled move when there's a force of the sled on the dog? There's a force of the dog on the sled. They're equal in magnitude and opposite in direction. Let me kind of like we know that there is, gravity is downward, and there was like a normal force upward, and maybe there's a little bit of friction pulling the other way. But mainly what I'm talking about is that there is this force. Let me zoom in so I could actually write this a bit clearer. So there's this force that the dog is exerting on the sled. Dog on sled. There's also equal and opposite force the other direction. This is the force of the sled pulling on the dog. Think of like the how you would feel if you were in that position, pulling backwards. So force of the sled on the dog. Why does anything move at all? Well, remember what we did on a similar problem with this, a couple lectures ago. We drew a free body diagram, and in order to do that, we had to narrow in on what we were looking at. So there's a whole lot happening here that isn't going to be included in a free body diagram. So if you specifically remember, I drew sort of this bubble around only what we were interested in. And in this instance, I would draw the bubble like that. So it would split these two things up like this. So now just looking at the sled, let's draw that free body diagram. We'll have it as just a dot. We have, of course, there's gravity. Of course, there's that normal force holding the sled up. Just gravity, normal force. There might have been a little bit of friction. We'll just say lowercase f for now. But then there's this larger force to the right. That's the force of the dog on the sled. And now it's clear that once we, zoom in on only what we're interested in, that's where we see where the acceleration happens. Since this is larger than that's friction, then we see that's how we're able to move things. We specifically look at that object only. If I was moving a fridge, if this was a similar picture of me pushing a fridge, the free body diagram would only picture the forces acting on the fridge. It wouldn't encompass everything in the picture. So it leaves out that whole other half. So maybe if you did have a question like that of why do things move at all, maybe that clarifies a bit. Okay, that basically sums up chapter 4. So that is all that is going to be on this upcoming quiz and all of the stuff that's on the homework that I have out already. So there's plenty, like there's dozens of examples in the book that I haven't even done myself. If you're having trouble with anything on Newton's laws, I'm going to start. I'm going to see how far I get with this next chapter for chapter 5. I'm not, as we move into chapter 5, I'm not going to be doing the whole chapter. I'm just kind of like pick and choose at a few topics that I want to cover. The first one is friction. So I think that it's valuable for everyone to know what friction is, how to calculate, since it is in a real world, in real world examples, friction is pretty much everywhere. So let's go on to chapter 5. So I'd consider this as like a half chapter. That's what we're going to do with chapter 5. So it's additional applications of Newton's laws. Okay, so the first one, or the first thing I'm going to focus on is friction. Specifically, let me zoom in. Friction is just a subtle force. This is sort of my own phrasing of this. It's a subtle force that opposes movement. So when one object tries to move near or on top of another object, the direction of friction is opposite to the direction of the object's movement or motion. So we could even classify two types of friction. There is static friction. Static friction it's interesting to sort of think about. So when something's sort of at rest and it is motionless, it has a different level of friction than when it's already moving. So static friction is when it's still static. stationary. I have a little picture that goes with this. I'm preparing to move this box. And I'm just sort of putting my hand on it. I'm giving a gentle push, but it's not moving. Okay, so I maybe push a little harder. It's still not moving. And I'll push harder and harder and harder. And perhaps you have, experienced this where, you could do this with something on your desk right now too. Something still, try to push it, and there's a moment where it's called like breaking free. So it will sort of take a lot of force to get it started. And then once it's started, it's a lot easier to actually push. So this is due to static friction. Let me write the equation and then I'll sort of dive into this picture a bit more. Write the equation that you need. So for static friction, we have the force, so it's a lowercase f, static friction. And specifically, since there is sort of like this, I could push a little bit. I could push this box. I could push, my phone on my desk. There's a little bit. I can push it up to a point until it'll break free. So I'm going to say S maximum is equal to, this is mu, this is a Greek letter. So let me try to draw it like a bit more. So it should look like this. Oftentimes, it might not. So mu of S, that's the coefficient of static friction times the normal force of the object. Let me, mu of S is coefficient of static friction. And what this means is every single object, every material has its own coefficient of static friction. And this is just a number. It's just sort of a scale that things are rated on. Now let me dive into the picture. So we have this box, or you think of it as like I'm pushing a refrigerator or something. I'll just say box. And I'm giving it a force that way. This box is resting on a surface, so it has a sort of contact with the ground. So where there's contact, there's a normal force. But let's look at, this is the floor. Let's look at sort of like a microscopic, viewpoint of where these two objects, the box and the floor, where they're meeting. So I'm going to make like a little circle. So imagine we zoom in on this little circle. So we're talking like with an actual microscope, maybe even on the atomic level. The molecules, maybe even the atoms, are structured in not a very perfect way. Even if this is what looks like a smooth cardboard box, there are tiny little jagged peaks and valleys in how the molecules are held together. So that's the box right here. And as something is staying still, you see these peaks and valleys of the the structure of the box, they can maybe mesh together with the peaks and valleys of the floor. So they're sort of like interlocking when something is still. And now maybe that makes more sense, that there's this sort of, large push you have to do to sort of break it free. So I'm going to say there's a limit, or I'd say there is a threshold. So the force of static friction is less than or equal to the coefficient of static friction times the normal force. And then underneath this, I will say why we are doing this, less than or greater than, or less than or equal to. I'll say if you exert a force larger than, exert a force larger than the force of static friction, then the object will begin to slide. All right. So we have this sort of, when things are still, they sort of lock together a little bit. That's static friction. Things are still, motionless. But then there's a point where you do break it free and you have this moving friction or this sliding friction. That is called kinetic friction. It's just barely overlapping. Let me fix that. Okay. And there we go. Kinetic friction is, you think of it as the moving friction. Kinetic means movement. So, it's a continuous opposing force. Assuming you're moving like the box at a constant speed. So let's do same type of picture example with someone pushing a box, but this time it's moving. We have a box. This person's applying a force, but now the box is now sliding. And I'll say constant velocity. So it's moving at a steady rate. It still has a normal force because it's still resting on the ground. But what is the sort of molecular structure? How are they able to move past each other if they are these sort of peaks and valleys that I've sort of drawn up here? Well, let's zoom in on it. Make a little slice like this. Sort of zoom in with a microscope. So in order for this object to start sliding, let me do that. the object still has its sort of, very irregular, jagged structure. This is the box on the top and the floor on the bottom. But now, since it's sliding, it's not perfectly interlocking with one another now. They're just sort of, the top object is quickly gliding over the bumps of the, of the floor. So since they're not completely interlocking, it's a less, it's a, a force that's slightly, smaller in magnitude. Let me draw, or let me do the sort of equation. Okay, this is the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. This is mu k. Of kinetic friction. Okay. These two values, coefficient of static friction and coefficient of kinetic friction, they are different. So one object can have a very high static friction, coefficient of static friction, but then a very low kinetic friction, coefficient of kinetic friction. Typically, this is the trend with most objects. That's why you push your phone on your desk. It's sort of hard to get started, but then as soon as you do start, it's generally easier. And these are just values without units, these coefficients. So these are just numbers. You could look up like a table if you're looking at like steel. So steel, it has a very low coefficient of kinetic friction. That's why it's sort of good for train wheels. Since it's steel on steel, there's very little friction between the two materials. So it takes a long time for it to get started because there's little friction. And it also takes a long time for it to stop. Let's go to the next page. So these are two like most common types of friction. I'm going to at least list this next one, which is rolling friction. And that is, I'm sure you see where this is going. Rolling friction. It's all of the equations so far have looked the same. This is the friction required for a wheel to roll. If you think about a wheel rolling on the ground, it is, fixed at one point on the ground. It's fixed at one point, and it gives just enough friction for the wheel to move to the right or left. So it gives just enough friction at this point for that wheel to move. And this is a different type of friction. It's called rolling friction. We have F, R. This one isn't too common in a lot of physics classes. It is a bit more specific. Maybe in like an engineering class, this would be more more prevalent. R, I'll do lowercase r, R times the normal force. All right, so we have this. Oh, I forgot to say. Coefficient of rolling friction. Okay. So we have several types of friction. Let me do one example that I think will take the rest of the time today. So let me try to get through this as quick as I can. But then in the next class, we'll go over center of mass. Okay, so for this, just about. Okay. Example. This example is going to use multiple parts with multiple types of friction. So we are preparing to pull a sled that is currently at rest on some snow. The sled has a mass of 50 kilograms, and you begin to pull the rope connected to the sled at an angle of 40 degrees above horizontal. The coefficient of static friction and kinetic friction are given here, 0.2 and 0.15. And the tension the tension in the rope that you are pulling with is first at 100 newtons and then 140 newtons. So what we want to know is, what is the magnitude of the frictional force exerted from the snow onto the sled? So basically, we just want to know like how much friction there is in general. Once the sled begins to move, what is its acceleration? Okay, so there's a lot to unpack here. Let me start with a picture. This picture is a bit too much for what we want, so let's do a free body diagram of what we see here, what we know so far. So I'll do it as just the dots this time. Or yeah, I'll do it as a dot. We know that's gravity. It's accelerating it downward or trying to force it downward. We know there's a normal force supplied by the ground. We know that there is some kind of friction opposing the motion this way. And we know that we are pulling it at an angle above horizontal. So that's sort of this theta right here. So that would be some kind of angle above horizontal. Let me just that. And that is the tension in the rope. Okay. While we are on this sort of planning phase, we already know we're going to split it up into components. So this is made of, the tension is made of an X component and a Y component. Y, let me put tension right there. There we go. Okay, so what we want to say, or what I'll have at the top, it's going to have to slide the question down so I could write in the free space. What's something that we could check is, does the horizontal force make the sled move? Does horizontal force okay, so we want to constantly be checking this static friction sort of limit. So we know it's at rest, so it has some static friction. So we're going to have to check this sort of rule as we go. If the question said it was already moving, we wouldn't have to do this. Okay, now that we have sort of a good setup, let's split this thing up into its components. Let me move this up a bit. So I'm going to go right here. So we have forces in the x direction. Plus, since we know it's stationary for right now, as it says at the top, it says currently at rest. So we're going to use static friction in the x direction plus t of x equals mass times acceleration in the x direction. Okay, so there is no normal force, there's no gravity. There is, in fact, let me make this a negative. There's a negative frictional force, static friction force that's going to the left. And there's a positive tension to the right. And that was, it's going to be t cosine of theta. That equals, since it's currently at rest, we want to see if it's going to move. So currently at rest, there's no acceleration. That is 0. So we can see, we can rearrange this as force of static friction in this specific problem is equal to tension times cosine theta. Now let's find the y component. Y equals same exact arrangement. F static friction in the y direction, tension in the y direction. Okay, so we have positive normal force, a negative force of gravity. There is no frictional force, vertical direction. There's a little bit of a vertical force of tension. But the object isn't moving up and down, so that is 0, no acceleration. Let's solve for the normal force right here. F sub n equals F sub g minus tension times sine theta. All right, so now here's the point where we need to sort of input some forces and see if the thing starts moving. So I'm going to go like this. And the first force that we are, exerting on the sled is 100 newtons. See up here. So this is what I'm going to say. We have to check. (100 newtons). And to do that, we're going to use this sort of rule up here. And I've conveniently already found the pieces to it. I have force static friction that will go in right here, and the force, the normal force will go in right here. Okay, so less than or equal to coefficient static friction times this. That becomes T times cosine of theta less than or equal to coefficient of static friction, F sub G minus T sine theta. And let me just input the values right underneath it so it's clear. So that's 100 newtons times cosine theta, or sorry, cosine of 40 degrees. This was 0.2. So that's 0.2 times the force of gravity. So that's just the mass of the sled, 50 kilograms times 9.8 meters per second squared minus 100 newtons times sine of 40. All of this shows me a relation of 77 newtons is less than 85 newtons. And what I get out of this sort of, proof or check that I'm doing, I see that this does hold true. So 77 is less than 85. So I say, so it's not sliding with 100 newtons of tension. Okay, so that's sort of our way to check to see if it does actually start sliding with the force we provide. So I know I'm going to run out of room, so I'm going to just shrink this middle section just a bit. So I'm going to put it right there. I'm going to move this one up. Now we're going to check for the other force that we are going to provide. So we do 100, and then we are going to go to 140 newtons. Okay, so we check 140 newtons. So I'm not going to rewrite the top part, but I will put the values in already. So that's 140 newtons times cosine of 40 is less than or equal to 0.2, 50 kilograms times 9.8 meters per second squared minus 140 newtons times sine of 40. We get a result of if you were to do the calculations on both sides separately, see that 170 is less than or equal to 80 newtons. And since this is not true, this breaks the condition. Sort of breaks the condition. So I'll say sled begins sliding. Okay. Now we kind of have our check done. We know that's going to start sliding at 140 newtons. Let's find the kinetic friction of this tension that we're giving. So let me shrink this top part a bit. Okay. So we have this force of kinetic friction. So now we know the sled is sliding. Then we could just put in the values that we've already solved for. Fk is equal to the coefficient of kinetic friction, mg minus t sine theta. This will equal, now remember we have to put in a different coefficient here. Coefficient of kinetic friction is 0.15. That's 0.15 times 50 kilograms, 9.8 meters per second squared, minus 140 newtons, sine of 40 degrees. All of this will equal 60 newtons. Okay, and we have, we still have to find, real quick, we have to find the acceleration. Now that we know it's the force, we need to find the acceleration. So let's look just at this x components. So I'm going to go like this to make a little separation zone for this x component when the sled starts sliding. We have a minus kinetic friction force. But then we have that force of the person pulling the sled. Okay. Ultimately, we will get an acceleration term. It looks like this. Okay, plus t cosine theta. All of that over mass. And to save time, we know what all these values are. We get an acceleration of 0.94 meters per second squared. Okay. So that is a fairly complex problem involving both static and kinetic friction. You see, there's this sort of, we know how to split something up into pieces, with just components, but now we need to also, check for conditions and also try different values. So there might be a different result. If we, pull the sled a little harder, then it makes sense that it will eventually start to move. Okay, so that's all for today. Tomorrow, I'm going to cover some center of mass, then pretty much finish this half chapter. That's what I'm going to call it. So other than that, if you guys have questions, always email me. But I will see you later.